This is a lecture for Math 107, Chapter 4. It is on the equations of limited growth. If you consider the exponential growth functions, you notice that as t becomes very large, as t goes to infinity, the function also approaches infinity. For example, if I draw a graph of it, I would start at a0. This is the value for the amount, and here's time t. That as t gets bigger and bigger, this function just gets bigger and bigger and bigger, going towards infinity. Well, that's not very realistic. Perhaps a little piece of it is realistic, but the overall trend is not realistic. What's more common is that something grows exponentially and then levels off. This occurs in bacteria, for example. So here's the amount of bacteria. It starts off exponentially, but then as it runs out of room and water and food, it sort of levels off to what this would be the amount of bacteria that the environment that it's living in can support. So it doesn't have, I'll change color here, it might start off like this, but then it going in that direction, but it changes. So what I'm going to discuss are equations that behave like this. This is a little more complicated than what I'm going to show today. This is the logistics equation. And it has one curvature here that's positive, looks like it's growing very rapidly. Then there's a point where it turns over and starts to level off and asymptotically approach some limit. We're going to do something simpler than that. And what we're going to talk about instead is what's called the creep function. And here is the creep function. Now notice it has, instead of a0, I put a max, and that's kind of a hint as to what will happen. Then in parentheses, multiplying this a max, which is a number, will be 1 minus a decaying exponential. And I put a note in the written notes and also here that when you're trying to understand how a function behaves, look at the extreme values of the function. Look at what it behaves like when t is 0. Look at how it behaves as t goes to infinity. That will give you a lot of information about the function. In fact, it is equivalent to making an engineering sketch. In engineering, or in physics, and actually math as well, when confronted with a problem, the first thing to do is make a sketch. Often if you make that sketch, the whole problem, the solution of the problem becomes apparent. On the other hand, if you cannot make some kind of sketch, you probably can't solve it. Okay? So making sketches and looking at functions in extreme values, those are very important things. So what we're going to do here is look at how that equation behaves. Let me write it again for you. So I said a, which varies with time, is equal to sum, I'm calling a max, times 1 minus e to the negative kt. T is time. Right, so let's look at it when t is 0. When t is 0, of course this whole thing is 0, but what's e to the 0? E to the 0 is 1. So in parentheses you have 1 minus 1, which is 0, and the whole thing is 0. In other words, when t is 0, the amount is 0. It starts off at 0. Now let's see what happens as t approaches infinity. That means as t gets bigger and bigger and bigger. Well, let me write that again for you. I'll just clear this board here, and I want to write again what we have. We've got a equals a max, which is just a number, and you'll see why it's called a max, 1 minus e to the minus kt, and we want to know what happens as t becomes very, very large, as t approaches infinity. Well, a max doesn't change. That's just a number. It doesn't care what t does. 1 doesn't care what t does. But this exponential, as t goes to infinity, what happens to a decaying exponential? Here's a decaying exponential. It starts at 1. Remember, it started at 1 right here. And then as time goes on, it just decays away, asymptotically approaching 0. Here's time. Here's your e to the minus kt. K is just some factor to scale the t. Okay, so it's going towards 0. So this term, and I can do an arrow like this, goes to 0. So this goes to 0. If that goes to 0, all you have in parentheses is a 1, and the answer is a max. So what this equation does, I'm going to erase this again. Here's time. When time is 0, it starts at 0. As time goes to infinity, it gets closer and closer to a value like that. That's why it's limited growth. So here's an example of an expression for terminal velocity. This kind of limited growth applies to the problems of terminal velocity. That's the velocity that you reach as an object reaches as it falls through the air. There's also charging of capacitors, certain properties in material strength as they're deformed. So this is it's related to the creep function. It's very useful. So this is our velocity, and we're putting a 50 out here. Okay. Of course, it's different whether you have a parachute or not. 1 minus e, and I've got t over 5. Remember that 5 is just a way to scale it, and I'll talk about that in a minute. Now, this is exactly the same as what we had before. Before we had a equals a max, and now the a max is substituted by a 50. You pretty much know what that should mean. 1 minus e to the kt. So in our case, k is 1 over 5. So what happens when t is 0? When t equals 0, oh, that's a negative sign. Sorry about that. E to the 0 is going to be 1. So you'll have 50, 1 minus 1 in parentheses, and 1 minus 1 is 0, so you got 50 times 0. So it's so much 0 it won't even write it. And the answer is 0. So here's your initial value. When t is 0, the velocity is 0. This has to do with the downward velocity. Okay. If a bolt or someone steps off an airplane and the airplane's going forward, the airplane does not have a downward velocity. We're only talking about the downward component of velocity, not the forward component of velocity. Okay. If you needed a downward component of velocity when you started initially, you'd have to add it on as a constant. But we're not doing that. We just want to study this equation. Right. So we start here with an initial value of 0. And now you know what happens from the previous one. As t goes to infinity, this function goes to a max. It approaches it asymptotically. So we've just drawn that in here with a dotted line. How you get the other values is to put it in the computer. You put it in the calculator. This exponential has a time constant of 5, so count by 5s. So put 5 in the computer, find out where you are. You're going to be quite a ways along. 10, 15, 20, and then 25. So you can plot those values. There's a problem about this in the homework. So you can plot those values, and this is what you should get. You should get it increasing, a big jump at first, and then it bends over and asymptotically approaches 50. This is an exponential. It has a time constant of 50. From other lectures in this chapter, you may recall that after about 5 time constants, most of the action is over on these exponentials. So here would be 5 time constants up to 25, and you can see that about this time the function is, there's not a lot of change in the function after that. Like I said before, this could apply to a terminal velocity, approaching a terminal velocity. It could apply to charging a capacitor, in which case this might be voltage. And we're saying that the capacitor is initially totally discharged, and it would follow a path like this. The 5 would change, of course, and what you're charging to might change.